Hello students, in this video we are going to continue with chapter 9 Force and Laws of Motion. Now let us do the numerical that we had left in our previous lecture. Example 9.5 NCERT textbook. I'll read the question, listen to the question properly. The velocity time graph of a ball of mass 20 gram moving along a straight line on a long table is given as shown in the figure. I have drawn the graph here. How much force does the table exert on the ball to bring it to rest? Now I'll read it again and you should be able to write what is given. See, graph is drawn here. Okay, this is a graph which is drawn in the textbook in the question. The velocity time graph of a ball of mass 20 gram. So what is given? Mass m is 20 gram. Moving in a straight line on a long table is given by this figure. How much force F we have to find out. How much force does the table exert on the ball to bring it to rest? To bring it to rest means final velocity we can write as 0 meter per second. Okay. Now I hope you have understood the question well. So this is a graph. We have to find the force. We know there is one formula for force. Force is mass into acceleration. Mass is already given here and acceleration we have to find in order to calculate F. So for acceleration we have to take the help from graph. First of all, let us see what is given here. Mass of a ball is 20 gram. And the ball is moving on a long table. It means distance travelled by it will also be not very large. So instead of taking SI unit, here I have preferred the CGS units. And hence I have written final velocity V is 0 meter per second, which is equal to 0 centimeter per second. So it depends on the question. You should read the question and you should be able to decide whether to find out the answer in SI unit or CGS unit when they have not mentioned anything. Now, let us have a look at the graph. We can solve this numerical by any of these two methods. From the graph, we can see that the velocity time graph is a straight line inclined to time axis. It means this is the graph of uniformly accelerated motion. And as the slope is this way instead of this way, we know that it is a case of uniform retardation. Velocity is decreasing. So first of all, let us use the property of the graph. We know that slope of VT graph gives us what? Acceleration. And so here acceleration A is equal to slope of the graph. Slope of the graph means perpendicular upon base. So perpendicular upon base is slope. And here what is perpendicular? What is this height? See, 5, 10, 15, 20 and the units are centimeter per second and second here. So this is 20 centimeter per second. Okay. And what is a base? This is a base. Okay. So this base is 10 seconds. So acceleration is 20 divided by 10, that is 2 centimeter per second square. I have put the negative sign here. You can also put it here also. Why negative sign is put? Because we know that velocity is decreasing. Whenever the velocity is decreasing, then the acceleration has to be negative. So you should write acceleration is negative minus 2 centimeter per second square. And now it is very simple to find out force. Force is mass into acceleration. Mass is 20 gram. Acceleration is minus 2 centimeter per second square. So the answer that you will get is minus 40 times. So force is minus 40 times. Why minus? Because it is a retarding force. It brings out uniform retardation. So this is a retarding force and hence it is negative. This is one of the methods. Other method what you can do is, see, have a look here. From graph we can see that initial velocity, this is initial velocity when time is 0. Initial velocity is 20 centimeter per second, so that is u. And then final velocity is this, is 0 here. Okay. So final velocity is, because this is 5, this has to be 0. So velocity is 0 centimeter per second. What is the time taken for this change in velocity? 10 seconds. So t is 10 seconds. So from the graph, we have got the values of u, v and t. So acceleration is by definition v minus u upon t. So we can put the values and again we can get the answer of acceleration that comes out to be same, minus 2 centimeter per second square. And then by the similar method we can find out the force. I hope this is clear to you. Now students, before we start with Newton's third law of motion, let us see that how Newton's second law of motion can be used to prove Newton's first law of motion. Hope you remember both the laws. Okay. Now Newton's first law of motion, what does it state? It states that every body continues to remain in its state of rest or of uniform motion along a straight line unless an external unbalanced force acts on it. It means, in other words, only when force is acting on a body, then only acceleration can be produced or then only velocity can be changed. If no force acts on a body, then the velocity will remain constant. And even the direction, so velocity will remain constant means direction of motion will also remain constant. And what is Newton's second law of motion? The rate of change of momentum of a body is directly proportional to the force applied and it takes place in the direction of the force applied. We know that from Newton's second law of motion, this is the result that we have got. We had derived this expression F is equal to ma from Newton's second law of motion. Now let us see how this expression, how this law can be used to prove Newton's first law of motion. Now here if I consider a body having mass m, which is initially moving with uniform velocity u. Let us say constant force F acts on it for time t so that after time t the velocity becomes v. Then according to Newton's second law of motion, I can write F is ma is equal to m into v minus u upon t. Hope this you remember, this we have already done. So you should write the introduction and you should write according to Newton's second law of motion, we have this. Now let us consider that if no force is acting on the body, if no force is acting on the body means no external unbalanced force is acting on the body. It means this F is 0. So suppose if F is 0, let us put the value of F as 0 in this formula. If F is 0, then we get left hand side is 0, so right hand side should also be 0. It means m into v minus u upon t is 0. But we know that mass of a body is a positive number and even time is here positive. So it both can never be 0. Okay. So here mass is always positive. T, if suppose we imagine that no force is acting on the body. So in that case we can take time to be equal to 0 also. So if F is 0, this right hand side is 0. So m into v minus u upon t is 0. And we know that this will be 0 when the numerator is 0 because 0 divided by any number is 0. So in this case m into v minus u is 0. And mass of a body is always positive, it can never be 0. So v minus u is equal to 0, or in other words this implies that v is equal to u. So when v is equal to u means final velocity and initial velocity of the body are same. So in other words, when no force is acting on the body, the velocity of a body remains constant. It means if u is 0, v will remain 0. If the body is initially at rest, it will remain at rest. And if the body is moving with some initial velocity u, then it will continue to move with the same velocity v. That is, here v is equal to u. It will continue to move with the same velocity. Velocity will not change. If F is 0 means if no external force is acting on the body. So in other words, from Newton's second law of motion, by taking F as 0, we are able to prove that velocity remains constant. So we are able to prove Newton's first law of motion. That when a body is at rest, it will remain at rest. If a body is in uniform motion, it will continue to move in the same straight line with the same uniform speed unless an external unbalanced force acts on it. I hope so you can prove Newton's first law of motion from Newton's second law of motion. Now let us see Newton's third law of motion. Newton's third law of motion states that to every action there is always an equal and opposite reaction. In other words, it means that whenever one body applies a force or exerts a force on some other body, the second body exerts equal and opposite force on the first body. Equal and opposite force means force which has same magnitude but opposite direction. So here action and reaction are nothing but they mean forces here. To every action there is always an equal and opposite reaction. So here we know that single force never exists. Whenever a force is applied by any body, at the same time the other body applies equal and opposite force on it. Okay? For example, let us try to understand this law. For example, while walking, how do we walk? When we walk, we push the earth in the backward direction, and earth in response exerts equal and opposite force on us in the forward direction, and hence we are able to walk. Similarly, when you think how we jump, while jumping, we push the earth in the downward direction and earth applies equal and opposite force on us in the upward direction, and hence we are able to jump. Swimming, you must have seen the swimmer. How does he swim? With his hands, arms and feet. He pushes the water backwards and water applies equal and opposite force on the swimmer in the forward direction, and thus the swimmer is able to swim. Motion of a rocket. See, when we consider rocket has fuel inside it near the tail area and that is burnt. So when fuel is burnt, hot gases are produced which are compressed under high pressure. They are allowed to escape from the nozzle which is near the tail side. Okay, so the gases, they come out with very high pressure from this side, or in other words we can say that from the rocket they experience very large force and hence they come out in the downward direction, and when burnt gases escape from this nozzle in the downward direction, they exert equal and opposite force on the rocket and hence rocket moves in the upward direction. So motion of a rocket is also, using this we can explain Newton's third law of motion. Recoiling of gun. Now you must have seen that whenever bullet is shot from a gun, bullet moves in the forward direction, and when bullet leaves the gun moves slightly in the backward direction. So bullet is moving in the forward direction, covering very large distance, and the gun moves in the backward direction but comparatively covering lesser distance. So we say gun recoils. When the bullet is fired from the gun recoils. Recoils means it moves backwards. So again this is a result of this only, that when the bullet comes out, so it is experiencing a force from the gun in the forward direction, and at the same time bullet exerts equal and opposite force on the gun in the backward direction. I hope if the question is given to you, state Newton's third law of motion and explain it by giving few examples, you should be able to now write this statement and explain it by giving at least 2-3 examples. Now remember students, in the this case or in any case when we see the force exerted, both the forces, action and reaction, actually there is any force can be called as action and the other can be called as reaction. These action and reaction forces are equal in magnitude and opposite in direction, but still acceleration produced are not equal. Why? Because F is equal to ma. So here I can write m into a of this bullet is equal to m1 into a1 of the gun, but mass of gun is quite large compared to mass of bullet. So their products, their forces are equal means m1 into a1 is equal to m into a, but the masses, there is a large difference in their mass, so acceleration difference will also be there. A heavier body, a body which is massive, which is having more mass, will experience less acceleration than the body which is having lesser mass. Similarly here we can say gases are lighter So they come out here in the downward direction. They will exert a force on the rocket in the upward direction. Although mass forces are equal, but acceleration produced will be different in that case also. Similarly, here when we walk, we push the earth, but we cannot see earth is getting pushed in the backward direction because earth's mass is huge compared to a person's mass. So acceleration produced in earth will be comparatively negligible compared to the acceleration produced in a person while walking. Okay, so we should remember that Newton's third law of motion gives us the result that single force never exists. Secondly, if I say you, these two forces are equal and opposite, still they do not cancel each other. They are not balanced. Why? Because they act on two different bodies. Remember, two equal and opposite forces are said to be balanced when they act on the same body. So if I ask you the question, why action and reaction, although they are equal and opposite, still they are not balanced? You should say, because although they are equal and opposite, but they act on two different bodies. For the forces to be balanced, they should be acting on the same body first of all. So I hope Newton's third law of motion is clear to you. Now let us see how, using one activity, how can you write an activity, explain an activity which will explain or prove Newton's third law of motion. This is just for the explanation. Now let us see an activity using which you can prove Newton's third law of motion. Now suppose if the question is state Newton's third law of motion and explain an activity using which you can prove it. Okay, so for that we can consider this diagram. Statement you already know. Now this diagram shows two spring balances. You know spring balances are used to measure the force exerted on a body. Actually, we will see this in the next chapter that weight of a body is force of gravity acting on the body. And especially spring balances are used to measure the weight of a body. And indirectly they can also give us mass of a body. But if I ask you what does spring balance measures, your answer should be weight of a body. Now here we have two spring balances. This is the first spring balance, this is the second spring balance. Now we know that spring balance has one fixed end and the other hook. Normally we hang it this way. Okay, this free end is fixed to some support, and then this hook is hanging down, and we can, using the thread, we can hang any body on the hook, and the reading on the spring balance will give us weight of the body. In this case, spring is not, it is not hanging vertically. What we have done, the fixed end of the spring balance we have attached to a wall or to a fixed support. So let us say we have a fixed nail here and we have fixed this spring balance here by using a thread to the nail. Okay. Now the free end of this spring balance is hooked by the free end of the other spring balance. Okay. So they are hooked together like this. And the fixed end of the second spring balance is pulled by someone. Let us say you pull it. Okay. So when this is pulled, what happens? This hook is pulled by the spring balance. When this hook is pulled by the spring balance, obviously when hook is pulled, this spring balance will show the reading. When the spring balance is hanging vertically, then the reading gives us weight of the body which is hanging. But in this case, when it is pulled, so this spring balance is now pulled by this spring balance. Actually, using fingers, using hand, we are pulling this spring balance, but the first spring balance will show the reading. It means through this hook, the second spring balance is exerting a force on the first spring balance, and we can see the reading here. But you will also see that here also the second spring balance shows the same reading. Let us say this is a pointer. So same reading is shown on the second spring balance. Okay, readings on the two spring balances are equal. What does it mean? It means that this spring balance is also experiencing force. How much force? Same force. Magnitude is same as that on the spring balance first. So this hook is pulled attached to this spring balance. It means first spring balance experiences a force by the second spring balance, and second spring balance experiences a force through this hook by the first spring balance. The two forces are in opposite direction. This hook is actually in this direction experiencing a force, and this hook is experiencing a force in this direction. So the readings show that they are equal in magnitude. So from this activity we can prove that as the two readings on the two spring balances are equal, as the readings on the two spring balances are equal in magnitude, we can prove that to every action there is always an equal and opposite reaction. So this activity can be written for proving Newton's third law of motion. I hope it is clear to you. Students, from now onwards we will not be writing the learning outcomes on the board at the beginning of the video, because I think so you should be able to get the learning outcomes yourself. You should only think after the lecture, you should think what questions you have understood, whose answers you can attempt. You should be able to form the questions and write the answers on your own. Thank you, students. Hope everything is clear to you.